Okay, so we left the with the graph, which was basically a straight line, dot dot dot, and this straight line, by the way, I want it to be x equals y, meaning that each, if we remember the points down here, at each point, say 1, at each point here correspond the same value on the other axis. This is y, and this is x. So this is the meaning of this equation, x equal to y. Okay, not considering anything below 0, let's stick to the natural numbers for the moment. Okay, so but we did a bit more. We had our rectangles. Okay, remember it's important to remember that they touch the line, because that's the approximation that we want to do. You can do also the other approximation from the bottom side, but let's stick with one and see where we go with this. Okay, nice. So first of all, I want 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6, and 7. Okay, so first let me highlight the red, these red areas, which let's say are, let's call them like errors or approximation, because what we are interested in doing is calculating the area below the curve. So the one that I'm going to highlight in yellow, for example, we want to calculate this area, okay, all of this area here, and okay, we know that already, but by just looking at this graph and remembering some basic geometry, let's say, we know that the area of a triangle is base times height divided by 2. In this case, the base count to 7. The height is 7 as well. 7 divided by 2 is basically 749. 49 divided by 2, which is 24.5. Okay, it's just a number. Let's see where we can get with the approximation that we've done, and I guess that's the target value that we want to achieve. Okay, so let me erase this guy. I will remember it later on. I can write it up here, 24.5. Okay, there are no unit to measure at the moment. We don't care. Let's play with it. Okay, so how do we calculate the, let's say, the red plus yellow area? Okay, red plus yellow area. Red plus yellow is just, as I said before, is the sum of the rectangles. So it's basically A1 plus A2 plus A3 plus A4 plus A5, A6 plus A7. Okay, all of these A's, we remember AI was a rectangle. The base of the rectangle is 1 because I chopped it in with integer, but the height changes with each rectangle, as we can see, according to the rule that we decide, which is x equals to y. So A1 is equal to the area, 1 times 1. A2 is equal to 1 times 2. And then A7 is equal to 1 times 7. Okay, so now where we can, so we, well, I'm not doing the multiplication, but basically we are summing, we need to sum all the i's, I equal 1 to 7 ai, and but this ai, if you see from here, are just the first 7 integers, so I can cancel this ai, and this is the label for the integer that I'm using, and this is I, the sum of the first 7 integers. I want to use a formula which is well known, has some nice historical, I don't know if it's a fact or a legend, but I can put the link maybe below in the upload for who is interested. But basically the formula says that if you sum, so when you sum the integer n from n that goes 1 to big N, the sum is n times n. Hope to not get it right. I will check later on. Divided by, I think it's plus 1. Let's see if it's correct. Okay, so from 1 to 7 is 7 times 8 divided by 2. Okay, 7 times 8 divided by 2, it's 56 divided by 2 is 25, 20, 28, right? 28, 56, should be 28. Okay, which is slightly bigger than what we have up here, which is 24.5. But we know that because we want only the yellow area. So this is let's say an upper bound for the sum. So how do we go on from? But you already see that this is very similar to base times height, because base is n, which is 7. The height is n plus 1 in this case. There is something that we need to adjust, but there is the divided by 2 here, which is already appearing. So how do we solve this puzzle? If we can say that is a puzzle, but let's so at the moment the connection with the integral is this nice sum that I put up there, and let's see if I can do a step further. I want to leave the graph there to remember that we are approximating the sum with this procedure. Okay, so okay, but I need a bit of space, so let's do this, and let's do this, let's do this, let's do this. Okay, so where is the connection of the integral? So first of all, let's remind ourselves that an integral, although I started with the sum, the summation symbol, usually an integral is written with an s, with the s symbol, an f, a function, and something called measure, which is the x, which is a small piece of something, a small piece of x in this case. So, and usually there is some labels here, or on the bottom or from the beginning to the top. Let's say that we, in this case, we are integrating one dimension. So let's say that we go from x0 to x1. Okay, so, and this is the usual, it's a notation that is you can find anywhere, and it's very common. Okay, historical notation basically. Okay, so, but we want to make a loose connection with the sum. I want to make a loose connection with the sum of the rectangles that I showed, and there is a connection. n. Okay, so let's see if I can convince you of this. So first of all, let's erase this one and remember that what are we summing here is bits of what are we actually summing are rectangles, okay? And excuse me, okay, this is doing some stuff and I don't know how to get out of this.